Furstenberg boundaries and the Kaimanovich-Vershik conjecture.
Thank you very much. I hope, is this too loud? No, it's fine? Okay. So thank you for coming, and thank you to the organizers for inviting me. It's a real pleasure to be here to help celebrate this occasion. I was actually last in Israel in 96 and 97 at the Institute for a special year in ergodic theory, and it's really nice to be back on this occasion. So I'm going to be talking about joint work with Yuval Perez. And if any of you, I will post this talk on my homepage later, I haven't done it yet, which has some additional proofs in it that I won't have time to get into. We also have a paper that's posted there, and we just posted our final version of the book, which has a chapter on this in case you're interested in reading the whole thing. So I'm going to talk about random walks, and let me just, for non-probabilists who may be in the audience, remind you quickly about some things. So here is the integer line, and we do a simple random walk, which means we just go left or right with probability half each. And so here's a graph of a random sample after 1,000 steps. And one of the things that is obviously interesting is whether, starting at 0, the random walk will be back at 0 with probability 1. And it's not obvious if you look at it, but it's true and not so hard to prove. And therefore, every integer, in fact, will be visited infinitely many times with probability 1. And so random walk is called recurrent. If we do a similar thing on the square lattice, here's a sample. It started here at blue, and it walked around. The red is the most recent thing. It's obviously harder to come back to the origin. But it will happen with probability 1, and again, every site will be visited infinitely often. Let's look at an extreme opposite example, the free group on 2 letters. So imagine this is the identity. This is A, B, A inverse, B inverse, and so forth. It's a free group, so there are no cycles with these generators. And now what happens if we do a simple random walk? So all 4 possibilities are equally likely at each step. Well, anytime we're not at the identity, there are 3 edges that lead further away and 1 that leads closer. And so there's a push away from the identity, and the random walk will drift off to infinity with a positive speed. Okay? So it's called transient. Every site will be visited only finally many times. So this is the topic I'm going to talk about, simple random walk on Cayley graphs. So those were Cayley graphs. So what does that mean? So xn will denote my simple random walk. And there's some group gamma, which is countable and finitely generated. There's some finite set S, which is symmetric. It contains the inverse of all its elements, which generates gamma. Gamma is the smallest subgroup of gamma containing S. And simple random walk means xn plus 1 is gotten from xn by multiplying by a random generator S, say on the right, all being equally likely, for simplicity. This can be done more generally, but for simplicity, I'll stick with simple random walk. And we'll start, say, with x0 being the identity. And if anyone ever worries about periodicity issues, you could just make S contain the identity. Okay, that's the context. And I just showed you some examples. So I talked about z to the d for dimensions 1 and 2, and Polio also proved that in dimension 3 and higher, it's actually transient, like we saw on the tree, but it's not as obvious as it is on the tree. And we made this observation that on the tree, we have even more than transients. We even have that it escapes at a positive linear speed. Now, those are kind of extreme examples of infinite groups. We're interested in infinite groups. And here's a very interesting class of intermediate groups, which were introduced in this context by Kaimanovich and Vershik. So these are called the lamplighter groups. They're restricted Reith products, but I'm not going to tell you the description algebraically. I'm going to give it in another format. So it's a direct product, a semi-direct product. Here is a direct sum, so there's only finitely many copies of Z2 that are non-trivial at any point. In other words, psi m is an element of this set. The set is simply the Cartesian product. Psi is in this direct sum, and m is in z to the d. And m is just a location which we think of as the location of the lamplighter. And psi tells us which lamps are on. Psi of x is 1, we think of as the lamp is on. Because it's a direct sum, only finitely many lamps can be on. The identity element of the group is when all lamps are off and the lamplighter is at the origin. Now, I haven't told you, so that's the set, that's the identity element. I haven't told you how to multiply these. Well, what I'm going to do is give you a generating set in order to tell you the multiplication. So the generators we use will be these. So 0 plus or minus EI means psi is all zeros, and M is one of the D coordinate directions or the negative. So there are 2D of those, and the other generator is 1 at the origin and 0 for the lamplighter. So what does this mean? If we apply to any configuration one of the first generators, one of the first generators, the lamplighter moves in that coordinate direction that's specified, and no lamp changes. If the second generator is applied, the lamp changes the state where the lamplighter is, and the lamplighter does not move. And those are all equally likely. Okay? So let me show you a demo in one dimension. Now, one dimension is pretty long, so it's wrapped around a bit. Here's the identity. The lamplighter will be in blue, and the lamps will be turned on in black there. Okay? And yellow is just to indicate where the identity is. So at each point, one of those things happen. There are 3 choices each time, all right? Because it's just one dimension. So let me also just speed this up a bit. Widen the range a bit. So that's what happens for a simple random walk on the lamplighter group, okay? We'll come back to this later. Any questions on the definition? All right. Now, the transients and the positive limiting speed that we discussed are examples of limiting behavior or asymptotic behavior, but those are events that have probability either 0 or 1, not in between. And there are many other laws you can think of that have that same property. So what do we mean by asymptotic or limiting behavior? We can describe it either via the invariant sigma field. So these are invariant with respect to the trajectory x0, x1, x2, and so forth of the random walk. So invariant would mean it's invariant under the left shift. Any such event would could be called asymptotic. Or you could also think about it in terms of the tail sigma field, the things that depend only on xn from n arbitrarily large. Now, it's a little inconvenient to have 2 notions of asymptotic behavior, but in fact, they turn out to be the same up to sets of measure 0. That's the theorem of Derrienic. So you can think about it either way you want. I'm going to stick with the tail. So a natural question is, when is the tail trivial? Does every asymptotic event have probability 0 or 1, and it's not anything else possible? Some variable behavior at infinity. Okay, that would be the question. Well, this question actually is very interesting for several reasons because of connections to other things. So Blackwell identified the tail with a space of bounded harmonic functions. So U, this is with respect to some generating set, U on gamma is called harmonic if the value at every point in gamma is equal to the average of its neighboring values with respect to that generating set. So constant functions are always harmonic. And you can look at speed either with expectation or not, but it's pretty easy to see that the sequence of expected distances at time n is subadditive, and so that this limit exists always. And so one thing that's very interesting is that we have these equivalences. The tail is trivial if and only if the only bounded harmonic functions are constant, if and only if the speed is 0. Now let's look at the examples that I started with in terms of whether they have trivial tail or not. If we have a recurrent random walk on a group, So that means the random walk is starting at the origin, coming back to the origin infinitely many times. And every time it makes one of these excursions, it's independent of what it has done before. So anything in the tail is also, in fact, in the tail of these excursions. And Kolmogorov's 0-1 law says that the tail of independent random variables is trivial. So therefore, the tail of the random walk is also trivial, which is probably intuitive, maybe for that very reason. Okay? Now, that says nothing about dimension 3 and higher for z to the d, but those groups are abelian, and there's another 0-1 law, which will say that the tail is trivial. So the increments, the changes of the random walk, you're adding plus or minus ei each time, which is iid. If I interchange some finite number of those, that will not change what happens after those changes are finished because of commutativity. And so, in fact, the tail is contained in the exchangeable sigma field, and the Hewitt-Savage 0-1 law says that the exchangeable sigma field is trivial. So again, in all z to the d, we have no non-trivial asymptotic behavior. Now, for the case of a regular tree of degree at least 3, what happens? The random walk goes off to infinity, but it goes off in some direction. You can imagine, say, if there are 4 for the picture I showed at the beginning, it's going to eventually end up in one of those 4 pieces and stay there forever. And each one will have probability a quarter, and that's an event in the tail sigma field. In fact, there are all these limiting directions or rays. So there's lots and lots of non-trivial behavior. Okay? So those are the extreme examples I started with. What about the lamplighter groups? The intermediate case. So let me go back here and just run this a little bit more, maybe a little bit faster. Can you think of any, does it look like there's any asymptotic behavior? That is non-trivial asymptotic behavior. Something that might or might not occur. Okay, well, maybe the demo isn't very informative. Let me show you this in 3 dimensions. So here, the L is, let's see, so I wanted to turn these lights off. Okay, that should help. I don't know how well you're going to be able to see. If you can't see so well because of that, yeah, you probably can't see. There's a red L here, which is where the lamplighter is. And, and that one is not even working anymore. Well, so just to show you this is 3-dimensional, I'll just rotate it around a bit. And I'll run the random walk a lot faster. So you might start thinking about what's going to happen for asymptotic behavior in 3 dimensions, okay? So that's going to be the focus of our question, talk, that question. Now, let's go back to the lamplighter in 1 dimension. So this is a group, and it actually has exponential growth. So why is that? Think about the subset where the lamplighter never moves left. He either changes the lamp where he is or moves right. And you can see that actually the number of possibilities after n steps is the nth Fibonacci number. And in fact, the order of growth of the group is the Fibonacci number. So it grows exponentially fast. Well, Kaimanovich and Vershik, they had an announcement in 79 and a big important paper in 83, showed that the tail is trivial on the lamplighter groups on z to the d if and only if d is less than or equal to 2. So in dimension 3 and higher, this is actually not hard to see. So if our random walk is denoted phi n, yn is the random walk of the lamplighter, and phi n is the state of the lamps, remember that in dimension 3 and higher, just on z to the d, random walk is transient. So every site will be visited only finally many times, and there'll be a final state of the lamps, which we'll call phi infinity. And that is an asymptotic element. It's like the asymptotic directions in the tree. So the entire sigma field generated by the final configuration of the lamps is part of the tail sigma field and is obviously non-trivial. Okay? Let me mention, this is interesting even in dimension 3 and higher, not from the fact that it has exponential growth, but these are solvable and hence amenable groups. So the question that they asked, a natural question is there any other asymptotic behavior besides the final configuration of the lamps? Or up to sets of measure 0, is that everything? And they essentially conjectured that that was yes, that was all. So that's actually the main question or conjecture that's mentioned in the title of the talk. But then they get back to their theorem. Why is it trivial in dimensions 1 and 2? Well, this is ahistorical, but after n steps in one dimension, the lamp lighter is certainly never is always between minus n and plus n, never gone outside, but in fact is very likely not to have ever gone more than some constant times root n. And so all the lamps that are on are also within that range, very likely. Now, what is the distance in the Cayley graph of such a configuration? Well, the lamplighter has to go and turn on all the lamps that are on and has to end up where the lamplighter ends up. But all this is within distance roughly root n. And so it takes only distance roughly root n steps in the lamplighter Cayley graph to do that. So in fact, the lamplighter, after n steps, is within a ball of radius roughly root n, and so the speed, distance divided by time, tends to 0. Which is quite interesting because it's an exponentially growing group. You can do this. You can show the same on z squared. The root n at the end turns out to be replaced by n over log n. And this is due to the recurrence, that the range of the random walk is growing sublinearly. Okay, now, there's another way to look at this, which is when the tail sigma field is not trivial. So I said that it was identified by Blackwell with the space of boundary harmonic functions, but it's not very concrete. So how could we describe all boundary harmonic functions? So let's go back to the classical case of the Poisson formula. We have the open unit disk, we have a harmonic function u, and with some conditions, there's some function on the boundary of the circle such that if you integrate it against the Poisson kernel, you can recover the values inside. Okay? So this inspired Hillel to look for a similar thing for groups. So first, let's give a probabilistic interpretation due to Kankatani and Dubh of that classical Poisson formula. So here's the unit disk, and here's a function over the circle, which is the Poisson kernel for z, that point there. And I've graphed it differently. It's easier to see in 2 dimensions. The function is graphed over the circle, so that's the height. Okay? The shaded part. Now, what's this stuff in the middle? So this is z. If I start Brownian motion here, and for non-probabilists, this is just a limit of random walks, which are very, very small steps going very, very fast. You wait until it gets to the boundary. And this red function is the density of the hitting place the first time you hit the boundary. And so the formula of Poisson just says that the value of the harmonic function here is the expected value of the function on the boundary of where you hit. And it also turns out that if you evaluate the function along the path of Brownian motion, you get the boundary value, almost surely. So here you have 100 Brownian motions starting from here that illustrate that average idea. Okay? Now, so that was a classical situation with Brownian motion. There wasn't an explicit group involved. So let's go back to discrete groups. The easiest one to understand is the free group. And there's an obvious boundary, which is a set of all these limiting rays, which look like all possible asymptotic behavior. And we could imagine defining a function on the boundary and recovering a harmonic function inside by taking the expected value of the hitting point functionally at infinity. So I'm not going to define, so this natural boundary of the tree is the Poisson-Furstenberg boundary. So Hillel called it Poisson boundary, and people sometimes call it Poisson-Furstenberg boundary. That's what it is on the free group. It's sort of evident geometrically. But what could it be for a more general group? Well, I'm not going to define exactly what these Poisson-Furstenberg boundaries are. I'll just give you these examples. In particular, restate in that language the conjecture that I mentioned before, that the Poisson-Furstenberg boundary of the lamplighter on z to the d, for d at least 3, is what? So z mod 2 to the z to the d. There's a 0 or 1 at every site. There's also this harmonic measure, this hitting measure, which is the law of phi infinity, the limiting lamp configuration from any starting point, say. So in that language, that's what the conjecture says. Any questions? Okay, now I gave an ahistorical presentation before, and in particular I skipped a very, very important notion, which is that of entropy. It's crucial to proving some of these theorems. So recall the Shannon entropy of a distribution on a finite set, P1 to Pk, is the sum of Pi log 1 over Pi, which remember is a most log K. Now entropy is additive for independent measures. So if I looked at all the increments of the random walk, those are IID, and the entropy of the distribution of all of them is just n times the distribution of 1, which is n times the entropy of the first step. Now, if we multiply, instead of just taking all a set of increments, we're really multiplying them xn, then the entropy of that is no more than n times the entropy of x1. So for those who aren't familiar with entropy, think of it as the uncertainty in the distribution. So entropy of the nth step grows at most linearly. Does it, in fact, grow linearly or not? Turns out to be a key question. First, there is, in fact, an asymptotic growth rate. Exactly. There's a subadditivity. You can see down here. So this is where we start to use the group properties. So the entropy after m plus n steps is most the entropy of xm and xm plus n, just adding more uncertainty. And now the entropy of the pair is equal to the entropy of the first one plus the entropy of the second given the first, which can be defined in different ways, but the way you should think about it is the expected entropy if you're given the location of xm. Now, if you're given the location of xm, you're taking n more steps. And anywhere in the group, you just take the same n multiplied by n random increments. So the entropy, no matter where you are at xm, is just the entropy of xn. So that's why it's subadditive. And therefore, by Feketa's lemma, the limit of 1 over n h of xn exists, which we'll call little h. This was introduced by Avez, and we'll call it the Avez asymptotic entropy. So, as a theorem due to these people listed there, which says that this Avez entropy is 0 if and only if the tail is trivial. Now, before, I showed you why abelian groups had trivial tail. Abelian groups all have polynomial growth. In fact, this we can use immediately to see that any group of sub-exponential growth has trivial tail. Because after n steps, the random walk is in a ball of radius n, and we're assuming that ball has sub-exponential number of points in it. So if you take the log and divide by n, it tends to 0. And remember that the entropy of a distribution is at most the log of the number of possibilities. So that's all there is to that. Now, I think I have time to prove this. Okay. So this is a very nice proof. Let's consider the entropy of x1 and xn. So we're going to do a similar thing as we did before, but without an inequality. H is equal to h of x1 plus the conditional entropy, which is h of x1 plus the entropy of xn minus 1. So we had that before. Or we could decompose the other way around. Start with h of xn and take the entropy of x1 given xn. Now, the Markov property says that even if we're given xn plus 1 and so forth, that's not going to change the entropy of x1. Because x1 and xn plus 1 and plus 2 and so forth are independent given xn. Okay. So we have two expressions for the same thing here. Let's subtract them and get something for this mysterious quantity here. H of x1 minus plus h of xn minus 1 minus h of xn. Now, let's take n to infinity. On the left, we are conditioning on a smaller and smaller sigma field, converging to the tail, and so in fact we get the entropy of x1 given the tail. So the way you think about this is x1 has some finite distribution, it has some conditional distribution given the tail, it has some entropy of that conditional distribution, and take the expectation of that, whatever it is. So now over here what happens? Well, this is constant. These are these differences. We know that the sum of the differences divided by n tends to h, and so the differences tend to h. Because they exist. We just saw the limit exists. Okay, so here's a nice relation. What does this tell us? Suppose h is 0, then this conditional entropy is the same as the entropy, and conversely. When is conditional entropy equal to entropy? If and only if x1 is independent of the tail. So that's a fact. I'm not going to prove. When is it independent of the tail? Well, in particular, it will hold if the tail is trivial. Everything is independent of a constant. So this shows one direction of the theorem. If the Avez asymptotic entropy is 0, then the tail is trivial. Now the other direction, we just modify what's in blue. Yes?
You showed the other direction.
What?
You showed the other direction.
How did I show the other direction?
So if the tail is trivial, then...
Oh, I said it wrong? Oh, okay. Sorry. If the tail is trivial, then the asymptotic entropy is 0. Yes. Sorry. Thank you. Okay. Now for the other direction. So let's abbreviate the vector x1 xk by x sub 1 through k. And just put that in place of x1 in the same argument we had up here. And when we come down here, what's going to happen? Here, we had n minus 1 because we went from x1 to xn. But now we're going to go from xk to xn, and there are going to only be n minus k steps left over. And by the Markov property, the ones before time k don't matter. So this changes to n minus k, which is a sum of k of those differences. And so this tends to the entropy of the first k steps plus k times the asymptotic entropy. So now conversely, if h is 0, then these two entropies are equal, and so the first k steps are independent of the tail. but that's true for every k, and the tail is a subfield of all steps. And so, in fact, the tail is trivial. Everything is independent of itself. So that shows that theorem. Okay, now the conjecture was, how do we identify the tail when it's non-trivial? Sorry, let me go back a second. So I want to say that you should think about this intuitively in the following way. H was its asymptotic entropy, which is the growth rate of the entropy after n steps divided by n. So you should think about the residual entropy after n steps is sublinear if and only if there's no non-trivial asymptotic behavior, right? Non-trivial asymptotic behavior says, is there uncertainty in what's going to happen in the limit? And so this is equivalent to saying how much uncertainty there is in the sense of entropy. So now we have a similar thing for identifying the tail sigma field when it's non-trivial. So suppose we have a sub-sigma field, which I'll call T prime, and we want to know whether it's everything. So the case we're interested in is like the sigma field generated by the final configuration of the lamps. Now, let's write H superscript T prime of xn for the following. Like we were doing before, we're going to condition xn on T prime. Xn has only a finite number of possibilities, so there's some random finite distribution, and take its entropy. So this is a random number now, measurable with respect to T prime. And you should think about it as xn given for the lamplighters given the final configuration of the lamps. So you're given the final configuration of lamps, and xn is some finite set of points. It was within some finite set of possibilities. Seeing what happens at infinity obviously biases the distribution. It's obviously hard to know what that is, but it's something, it's got some entropy, depending on the final configuration of the lamps. Okay? So, criterion of Kaimanovich is very similar to that theorem that I showed you before, which says that, first of all, this also has a growth rate, divide by n and take a limit. Turns out, although this was a random number, this limit is constant, almost surely. And it's 0 if and only if t prime is t up to sets of measure 0. So the way you should think about this is the residual uncertainty seeing t prime. Residual uncertainty in what? In the final, in asymptotic behavior, the final behavior, in terms of what could be described. Is there anything else that's uncertain about what happens at time infinity? And it says no, if and only if you've basically conditioned on what happens at time infinity. But in particular, if t prime is trivial here, this reduces to the preceding theorem, that t itself would be trivial if and only if h is 0. Now, this turns out to be an extremely useful and powerful criterion, but it's not obvious how to apply it because it involves these conditional entropies. And who knows what the distribution is of xn given some t prime. Well, Kaimanovich gave some useful corollaries. This is one. That makes it much easier to apply. It says the following. Suppose that Qn are some random finite subsets of the group that are measurable with respect to t prime. And they have the following two properties. They grow sub-exponentially fast in n, almost surely. And they capture asymptotically where xn can be. Probably the xn is in Qn tends to 1. Then, if you can do this, t prime is t up to sets of measure 0. So what's the intuition? The intuition is xn has only the size of Qn number of possibilities up to a small set of small measure, which is only a sub-exponential number of possibilities, conditioning on t prime. And so the entropy in the limit should be 0. Just like before with the case of groups of sub-exponential growth. Now, Yuval and I have enhanced this corollary a little bit. That makes it even easier to apply. So suppose I have these random finite sets that are t-prime measurable, grow sub-exponentially fast, but instead of requiring that xn be in qn with high probability, we're going to require that at some time m after or equal to n, xm is in qn. And with limiting positive probability, say. All these could be modified. If you can do that, then also t prime is t. Okay. So here is the answer to the conjecture of Kaimanovich and Vershik. First of all, Erschler in 2008, published in 2011, showed that in dimensions 5 and higher, I was correct. The final configuration of lamps gives you all of the tail up to sets of measure 0. And then we completed that to the full thing in dimension 3 and more. Now, if you think about how we would apply the corollary to find these random finite sets, that means you want to give a sub-exponential possibilities for xn that's likely to be where it actually is with high probability. Now, the lamplighter element of the group is a location of the lamplighter and a configuration of the lamps. The lamplighter himself can only be within a ball radius n. There are only polynomially many possibilities for that. You don't even need to look at what happens at time infinity. It's completely trivial to guess where the lamplighter is. Take all possibilities. But which lamps were on at time n? Well, there are exponentially many possibilities, even more, but we're allowed to use the limiting configuration, right? You see which lamps are on at time infinity, and now I want to say you get a sub-exponential number of guesses, which ones are on it at time n. It's not obvious how to do that, and it turns out to be easier to actually apply the enhanced corollary to do such a task. So here's our proof. We are going to find an event that makes it really easy to tell what happened at some time n or later. So I'm going to call this event cut sub r, depends on the radius r. This is the picture describing the event. It says that the lamplighter, that's yk, up to some time m, is within the ball of radius r, and after time m is outside the ball of radius r. Never comes back. Okay? That's the event. This does not have high probability of happening for a fixed m. However, I'm going to skip the technical outline, but the important conclusion is that starting from the identity of the lamplighter group, for the random walk, starting from the origin of just the random walk, yk, that one of these events occurs for r between n and n squared has probability bounded away from 0. Now, if this event happens, it's very easy to tell what lamps were on at that time m. So here is our set Qn. It's going to depend on the final lamp configuration. It's a set of all elements of the lamplighter group, phi y. Now, y is going to be a distance between n and n squared from the origin in z to the d. What is phi? Which lamps were on? Well, for inside the ball of radius, the distance of y, it's going to be whichever lamps are on at time infinity or off. It's exactly the same as the configuration of time infinity inside this particular ball, and outside they're all off. Now, so I said that the probability of this event is bounded away. Let's look at this event here. That there's some time m, at least n, for which xm is in this set qn. That's the event that we were interested in. Well, what happens when one of these spheres are cut spheres in this range? Well, the only way that can happen is for the random walk to this m that's defined in the definition has to be at least n, because its radius is n or more. And so the random walk has that property, and at whatever time m occurs, it is m. Yeah, this I think is missing something. No. All right. We're not saying what time this is. This is just the location. So this location is at between n and n squared. And if that happens, we don't know what time it is, but if the location is between n and n squared, then all the lamps that were on at that time, whatever time that was, which is unspecified, are the lamps that are on time infinity, and all the lamps that were outside are off.
Sometime after n.
Yeah, sometime after n. Now, how big? So that's part of what we wanted. Now, how big is this set Qn of possibilities? Well, it depends on y. Given phi infinity, the only remaining choices are what is y. Y is a distance of most n squared, and in dimension d, that means there's a most c n to the 2d possibilities. So that's the size. It grows only polynomially, which is even better than sub-exponential. So the enhanced corollary implies that the sigma field generated by the final configuration of lamps agrees with the tail up to sets of measure 0. So other than proofs of some things I didn't prove, that's all I had to say. So thanks for listening.
Thank you very much. Questions?
Yeah, organic group for polynomial growth. Okay, so you could probably carry through this method of proof for other groups, but we have a different method that doesn't use the enhanced corollary. And so the conjecture that the final configuration lamps is the entire tail holds for all groups, in fact. And you can also go beyond simple random walk in various ways. But different settings require somewhat different proofs.
But this particular thing right here is specific to polynomial growth.
This method is specific to polynomial growth.
The fact is easier when the growth is higher, but it's not as useful because when you use it, you use the factor. But it's true.
Well, this at the end, down here.
The problem is at the end.
The thing in red is true, or
Yes, but
Is it true that this proof good for the case when your number of states of lamps is infinite?
This proof works for that, yes. And most of our other proofs also work, even sometimes without the lamp group being finitely generated, as here. That has all the additional proofs that I said I didn't have time to get into. But I'm happy to give you a proof if you want to ask about one. Yeah, that has some supplementary material, so when I post it, if you want to look up some more proofs, they'll be there.
sense of comments? I don't.